Another little demonstration here. I think you saw with this that something happens, right? There's a current generated. I think we saw that. One way to think of it was the force on the charges. Another way was that there's an EMF generated, and that causes the charges to move. So what I've got here is a coil of wire, and I'm going to run current through it. And in this case, my current is changing. So the magnetic field that's created is going to increase and then decrease and go down and then come up and increase and decrease and go down because the current is always changing direction. And so if I just hold something right over the end here. Now first let me tell you what this is. This is a light bulb, and the connections on the light bulb are hooked up to a wire that's wrapped around and around and around in this circular loop. So there's no battery, just a light bulb hooked up to a loop of wire. But if I can create a changing magnetic field through the center of this loop, then that acts like a source of EMF. It acts like a little battery, a potential difference. And let's see what happens to our light bulb. You can see there's nothing else touching that light bulb. Okay? In fact, a lot of some devices use this to generate to charge them. So electric toothbrushes, maybe you notice they don't like to have the electrical contacts because they're used around water. They don't like to have the electrical contacts exposed. So there's a coil of wire in the bottom of your electric toothbrush. There's a coil of wire in the charger. You set it down on top, and the energy gets transferred to the coil in the toothbrush. Instead of lighting a light bulb, it charges a battery. You let it sit there, it charges up the battery, and then you can take it and use it. And some devices now have, my phone has the built-in wireless charging built into it. So there's some kind of loop of wire in the back of the phone. You set it down on top. You don't have to plug it in. You just set it on top of the charging base, and it inductively charges like this. You just pick it up, walk away, your phone's charged. All right. So what happens? We've got a loop of wire. This was a loop of wire, but I've got another one here. It's a conductive piece, loop of wire, basically, a big heavy wire. And this is an iron core. Why do we use iron cores? It intensifies the magnetic field. Let me show you why. You'll often see this with solenoids. We've got a solenoid here. Here, 4 turns. The current coming out on one side, in on the other side, the magnetic field doing this, right? That's B from the solenoid. Now, if we do this, solenoid plus iron core, then what do we have? We've got our 4 loops from the solenoid. And so the solenoid, and then we have an iron core in here. The solenoid creates its own magnetic field, right? And the iron core, I'll draw that one in red, in the iron, the domains, when that external field is turned on, the domains want to align with it, right? So now it acts like a magnet, and it creates its own magnetic field. And so the total field is the sum of the two, right? It intensifies the field from the solenoid. So here's this. Here's my my loop of wire. So what's going to happen? I'm going to turn on this is my solenoid. I'm going to turn on a current. Here, let me do it this way. Hold on. Okay, I close that switch. I get a current that comes out on this side, goes in on this side. And so what happens? I now have a magnetic field that points like this. A second ago, I didn't have it. Now I have a magnetic field that points like this. Now I have a loop of wire, or a ring, my metal ring. Let me draw that in red. I have a metal ring sitting on top. There was no magnetic flux a second ago. Now there's a magnetic flux pointing up. What direction is the current going to be generated in that ring? It's going to try to oppose the change, right? It's going to try to get it back to zero. So it's going to create a magnetic field that points down. So it would have to come out on this side and go in on this side to create a magnetic field that points down in the middle, right? It's trying to oppose the change. So what did I say? Out on this side and in on this side. So its magnetic field is going to go down. So what are those two magnets going to do to each other? They're going to repel each other, right? Let's see what happens. You ready? Repelled. Where's my mark? There it is. One more time. You ready? Got to make sure there's no light above me. All right. So I want to show you that it's the current in here that's caused. There's an induced current in here. The induced current makes this act like a magnet. Magnets repel. So I have a second loop. Looks pretty much like the first loop, except there's one minor difference. I cut a slit in this one. All right. So this one, no current will flow. This is an open circuit, right? There's a cut in it. Current's not going to flow. This one, current does flow. This one jumps. This one doesn't. Okay? I'll flip them around the other direction. The one that jumped pushed the other one off, right? But this one, because there's no current flowing, it doesn't have the same effect, right? It's the current that gets generated, acts like a magnet, they repel, and we get that jumping ring effect. Okay? So a couple of examples in the book. Speakers. you ever open up a speaker, what does it look like? You've got a big diaphragm like this, right? And on the back side here, there's a magnet. Something like that, right? And then what does this mount into? It mounts into something that has a coil of wire on it. So how do you make sound? Sound is caused by something vibrating.